The Lunar Compass. This is a method I've developed that uses the moon's shadow to orient to north. I've also developed a mathematical formula to predict the angle of the shadow as the moon crosses your local meridian. To describe the physical meaning of this angle, we will invoke a new term, the local orbital angle. This video will proceed in two parts. First, we will address what you will see in the sky, describing what to expect and how to utilize the lunar compass method. Second, will be demonstration of the physical premise upon which the method is based. Because this method is most accurate when the moon is crossing your local meridian, we will focus on this circumstance, where the meridian is simply the line running north-south through your local sky. It's equivalent to the line of longitude on which you reside. Now, as the moon traverses the sky, the angle of its shadow appears to rotate, where this rotation is most pronounced as it nears your local meridian. This motion is not random, but fixed by Earth's daily rotational motion, coupled to the moon's position in its orbit around the Earth. We'll return to this point later. For now, focus on the moon crossing your meridian. Here, the shadow will be confined to some angle between 23.5 degrees east of north and 23.5 degrees west of north, no matter what. Regardless of your location on Earth or time of year, it simply doesn't matter. However, I can now give you the ability to predict what that angle will be on any given day for any location. The formula for the local orbital angle is 23.5 times cosine of the RA of the moon, where 23.5 is simply the value of Earth's axial tilt. Cosine is the common trig function. RA is the right ascension of the moon. Right ascension is simply a device astronomers use to indicate an object's position around the Earth. So this indicates the daily position of the moon in its orbital path around the Earth. Any given day will have a unique RA value for the moon. Simply search this value for a specific day. Lastly, you will need to convert from hours, minutes, and seconds into degrees, either with an online converter or the conversions I'm presenting to you now. Now, because cosine oscillates positive and negative, this is how to interpret the results. When positive, this corresponds to an angle rotated west of north, while the negative value corresponds to a rotation east of due north. Obviously then, 0 degrees means the lay of the shadow at the meridian will be aligned with north. Now thus far I've been using the first quarter half moon to visually demonstrate, but this method is not dependent on the half moon phases. We can just as well utilize either of the crescent moon phases, and similarly can call upon the gibbous phases. However, because this method requires a utilizable shadow, neither the full moon nor the new moon is suitable for our use. Now with the first and third quarter half moons, it is fairly obvious that we draw a line along the straight edge of their shadow to determine the angle of rotation both expected and observed at the meridian. With the crescent moon, you draw a similar straight line by connecting the horns. And likewise, we can obtain our straight line with the gibbous moons. To be honest though, as the gibbous phase gets closer to full, it becomes more difficult to identify a utilizable shadow. So be aware of this method with the phase close to full. As an example, notice how the crescent moon can be used. It is quite straightforward to visually identify the line connecting the horns and determine the local orbital angle from this line for the various angles of rotation from north you could see. Now at this point you are ready to utilize the lunar compass. I encourage you to test the concept. Does the shadow really make some angle near the meridian? And can you actually predict what that angle will be? Now for your experiment, you will only need 3 things, which are all easily searchable. Let's demonstrate. First, determine what phase the moon is in. Remember, a phase close to full may disappoint, though waiting a few days will solve the problem. Second, what time will it cross your local meridian? Admittedly, it may not always be convenient, but it's easy enough to find websites where you can look ahead and plan accordingly. Lastly, determine the RA value and make your calculation for the angle expected. Using my example searches, I found a waning gibbous, which was really closer to 3/4 half, with a 6 a.m. crossing, which was doable. The right ascension converted to nearly 40 degrees, giving me an expected angle of 18 degrees. So, I'd expect to see a nearly 3/4 half moon whose shadow would be rotated about 18 degrees west of north. West since the value was positive. Again, you are now ready to implement the lunar compass. Please go test the concept for yourself. Now, let's consider what this angle physically represents. I've termed it the local orbital angle, but what does this mean? To understand the physical premise, we will use the celestial sphere, where, instead of describing the Earth's orbital journey vis-a-vis our motion around the Sun, it's more convenient to fix our location and consider how celestial objects appear to move around us. The horizontal, then, is described by the ecliptic, or orbital plane. Both the Sun and Moon occupy this plane. Here, the Sun takes 1 year to traverse the plane. Therefore, the year can be described by the Sun's various locations around the orbital plane, with several key dates indicated, while the Earth rotates once daily on its axis as indicated. Notice, typically the sky is what is allowed to rotate in this construct, but for us it's easier to consider our spinning, and the results are the same. Now, the first thing to realize is that although the Earth's axis is tilted at a fixed angle of 23.5 degrees, there are only 2 positions in our daily rotational path where your local east-west axes are oriented at this maximal angle relative to the orbital plane. As our daily rotational motion takes your locality into, then out of these positions, your east-west axes make a decreasing angle with the orbital plane, as indicated on the diagram. Therefore, there exist 2 positions marked in blue here where your east-west axes are actually oriented parallel to the orbital plane. As you can see, these are the summer and winter solstice positions of the Sun, while at the locations of the spring and vernal equinoxes, marked in red, your east-west axes are oriented at their maximal angle of 23.5 degrees relative to the orbital plane. So what we are seeing here is that during our daily rotational motion, the orientation of your east-west axes will oscillate between being parallel to and making a 23.5 degree angle with the orbital plane. Now, let's use a less busy diagram and consider how the moon's shadow is oriented relative to the orbital plane. To be definite, let's consider the December sun and 3 of the moon's phases. Notice here that the phases do not impact the vertical orientation of the shadow. This is because the sun and moon occupy the same plane. Finally, consider the spring sun around March 21st. Notice that all we do is slide the configuration horizontally in the plane, and that this has no impact on the vertical orientation of the lunar shadow. What you're seeing demonstrated then is that neither the time of year nor the lunar phase change the vertical orientation of the moon's shadow relative to the orbital plane. Now, at some point, your location will pass underneath the moon, this being when it crosses your meridian. At this point, your east-west axes will be making some angle with the orbital plane, as we previously saw, while the moon's shadow will remain vertical to this plane. Therefore, any difference in your east-west orientation away from parallel at this point will be reflected in the observed angle of rotation away from north of the moon's shadow. Or simply put, the local orbital angle is equivalent to the angle your local east-west axis is making with the orbital plane. As a last example then, you can see how the observed angle of the shadow will appear in your sky to be either aligned with or rotated away from north for the positions of minimum and maximum for several examples of the possible lunar phases. This has been the Lunar Compass. If you've appreciated my ability to observe what others look at but none see, then please subscribe. I'm only getting started. And consider participating in my little social experiment. The only way others like me will begin sharing their unique abilities is if people like you demonstrate its worth to them. Next time, I will deduce for you the true shape of the B-21 Raider, guaranteed.